Greetings, everybody. Let's finish our discussion on the connection between irrotational vector fields, conservative fields, and path independence. So kind of remembering a little bit from the last video that we talked about, we had this vector field f, which was negative y over x squared plus y squared, x over x squared plus y squared. We saw that that one, we had this potential function f of xy being arctangent of y over x. If we took the gradient of that thing, that gave us our vector field f. But we did a line integral over around our unit circle, and that thing ended up being 2 pi. But the fundamental theorem of line integrals said that if this thing was just the gradient of some potential function, that ought to be 0 because of path independence. So what exactly is going on here? Well, the answer to this is the piece that we're really missing in order to make the connection between irrotational vector fields and path independence. And that last simple piece that we've got is this concept of being simply connected. So remember that we talked about this several videos ago. That simply connected really just means that every loop in the region that we're interested in, we can contract that thing down to a single point. And so in particular, this thing really doesn't have any holes in it. Now, the region over which we actually integrated, the region for our circle, remember this thing was going to be defined everywhere except at the origin. And so this region that we have is not simply connected. That if I have this loop, if I put another kind of loop around there and I try to draw that thing into contract that thing down to a point, I can't because I'm missing the origin. I can't get around that origin. It's a hole that's there. And so that's the thing that's really causing the problem. My region has a hole in it. So what does this have to do with Green's theorem? Well, the boundary that we actually have kind of in this situation, we can think of it as really being two separate circles. Now, what Green's theorem told us was that if we had the curl of f over dA of our region D, that was going to be equal to the line integral over the boundary of this thing. And if we kind of expand this back from being a point just a little bit, if you'll allow me to do that. So expand this back from a point just a little bit, then what this really means is the boundary of D, we can break it up into kind of 4 separate parts. That we've got this first point, C0, that goes over to this point. Then we've got another curve, C1, that takes us into the inner circle. Now we're orient this thing positively, so we want to keep our region over to the left, so that means we're tracing this one out clockwise to get around through there. Then we come back to the point that we started, and now this thing, we're tracing it back through there. So we're tracing it back around C1. So we've got C1 and negative C1 because we're reversing the orientation on that one. And then we come back to this curve C3 to get us back to our original starting point. And so our boundary of D looks like C0 plus C1 plus C2 plus a negative C1 to get us back out, and then plus our C3. So that the C1 and the negative C1s kind of cancel each other out, and so our boundary ends up just becoming C0 plus 3C for the outside circle, and then C2 just for the inside circle. So what we actually do have is the integral of the curl. Well, we calculated that curl, it was 0, so this gave us 0. This was equal to our integral over the boundary of f dot dr, but the integral over that boundary, we split that up into 2 separate ones. We've got the integral for the outside plus the integral for the inside circle. So the inside circle has that negative orientation on it. Or it's got that, so it's the circle traced clockwise, and it's not really a negative orientation. It's traced clockwise so that we're keeping our region over to the left. This is the one that we computed before. It was the integral for the outside circle. That one ends up being 2 pi. So plus this other integral that we've got, this integral over our inside circle with a clockwise orientation to it. And so if we just take any old circle, doesn't matter, one that's kind of inside our unit circle, we can take a parameterization going in the right way, going clockwise. We can take something like 1/2 cosine minus 1/2 sine. So we've got a circle of radius 1/2 between 0 and 2 pi. But now this one, since that negative is in there, we're going clockwise as opposed to counterclockwise. So we're keeping our orientation. Computing our dr, we get a minus 1/2 sine, a minus 1/2 cosine dt. Plugging in our function values. So our x value is 1/2 cosine minus 1/2 sine for y. We put those in there. We get a 1/4 on the bottoms, a minus 1/2 on top, and so we end up with 2 times our negative sine, negative cosine. Doing our f dot dr, we get 2 times this one dotted with our minus 1/2 sine, minus 1/2 cosine, ends up giving us, so the 1/2s cancel with the 2, sine squared plus cosine squared just gives us a minus dt. So if we do our integral over C2 now, from 0 to 2 pi of negative dt, we just get a negative 2 pi. And so what does Green's theorem actually tell us? It does, sure enough, give us a 0, and that 0's being our boundary that we computed, our C, 2 pi plus a negative 2 pi. And those do end up canceling out to give us the 0 that we think we should have. And so kind of taking holes as being points and holes and points as being equivalent, this example that we have kind of now makes sense, that contracting things down to points, our original example, we didn't have actually all the boundary that we had. The hole actually gives us a second boundary that kind of, or a second part of our boundary that kind of messes things up a little bit when we start doing these things with conservatives. Talking about our simple closed curves. And so now this example kind of gives us the direction that we need and why we need this extra condition of being simply connected to show how all of these final pieces kind of start fitting together. And so to bring this all back, now we've got, if we're a conservative vector field, that's going to be equivalent to being path independent by our fundamental theorem of line integrals. Clairaut's theorem says that if we're conservative, continuous second partials, that's going to give us something that's irrotational. If we take irrotational and throw in simply connected, so that we don't have kind of these hidden boundaries for our curves for these holes that are actually there, then Green's theorem actually gives us that this thing is going to be path independent. And so we have the loop for how all three of these concepts end up fitting together. And now we've got a total picture of conservative, path independent, and irrotational vector fields all kind of together in one package. Awesome, awesome. It's kind of one last note that we've got in there. So what about this little function, our potential function f? Well, this little potential function being arctangent of y over f, that thing did give us the gradient of f. Well, where is this thing really coming from? We're talking about all possible lines through the origin. And those things are going to have the form y is equal to mx. And so the tangent of theta is actually going to give you your slope. The only place where we really have problem distinguishing any of these lines really come from the origin, because the origin is like the only point that's actually common to all of those lines. So we get this real problem point here at the origin distinguishing these lines. And so that's really where our potential function starts breaking down. We've got this problem here at the origin. And so even for our function f being negative y over x squared plus x over x squared plus y squared, if we take anything that doesn't go around that origin, then our potential function is going to be fine. We may have, if we cross over the y-axis, then we could have some zeros down here, but y is not going to be there. Our arctangent, if we are a little bit careful about how we treat that thing, even with the arctangent just being with that vertical line, in that case, as long as we're not going around the origin, we're not dividing it up, we're always above the y-axis or below the we're always above the x-axis or below the x-axis if we're not going around that origin. And so we can work out those kind of fine details, and the only place that really matters is that we're not going around the origin. In that case, our vector field is going to be conservative. We've got a potential function. Everything in this region we can shrink down to a point. We've avoided our problem point, and so we would get that the integral over c in that case was going to be 0. And so kind of this brings to a close our discussion of three of our really big concepts: conservative vector fields, path independence, and being irrotational. So I hope you guys that have enjoyed this series of videos, and I will see you guys for the next concept.